So this is a super interesting research paper that came out recently that caught my eye. It's called VPTQ, Extreme Low Bit Vector Post-Training Quantization for Large Language Models, and it's put out by Microsoft and University and Science and Technology of China. And the paper itself is a lot of mathematics. It's a lot regarding exactly what they're doing and regarding clustering and reshaping and grouping. And then you can see a lot of calculus here, and then a lot more here, an explanation, a full explanation of their algorithm, etc. And I'll leave a link to the paper in the description of this video. And it's a great paper to read through, especially if you want to know all of the full math and the methodology behind their full research. But I've recreated their research here in a simplified manner in Google Colab. And then so I can go ahead and kind of fully explain in this manner exactly what is going on in the research paper. And I think this is the easier way to explain it overall. So first of all, we need to understand exactly what vectorization and word vectorization is, and then I'll explain exactly what is going on with their concept. So as a high-level concept, we first take word vectorization. So for example, if we take the word vectorization and the word vectors for the word cat, like for this would be like IDF word vectorization, and then we would get like this as the word vectors for cat. And then so in this instance, so these are our word vectors, and then the very first thing that we do, it's interesting to me, it's like inception of machine learning, right? So step one, we use machine learning to get our word vectors. Step two is that we use a different machine learning algorithm. We use k-means clustering to find the center of these word vectors that are created. So in this instance of cat, there's associated words with cat, right? So there's like it would be the characteristics that make up cat. So it'd be like feline, the species that it is, the colors, whiskers, things like that, like all of these concepts, right? And then so all of these concepts are ancillary, and they're floating around this word cat. And then so whatever is in this cluster of cat, in the neural network, within the parameters, we use a k-means clustering algorithm to find the center of that. And I don't know what it's different for every model, right? But so whatever it is, and for whatever word it is, we say, okay, find the center. And then it does that. And then we say, okay, so here's the center of let's take this center and then let's break it into like broad categories. So rather than looking at like the full description of cat, you'll take the features of cat as a category, the genus of cat as a category, and we're going to take a few of those categories, and then we're going to use that, and then we're going to cluster that and simplify down to that essentially. And then what we're going to do is take the k-means average of this cluster, so the average of this cluster, and then we're going to convert it into like a table. So we'll say that this is 1, this is 2, and then this is 3. And then we have a lookup table, and then we look up 1 equals 0.445, 2 equals 0.56, and 3 equals 0.12 according to our lookup table. And then that's how we get our word vectorization that comes back out. And that's the full process that they're doing here. So really straightforward. I've built out this process here for you. So if this is still confusing for you, I'll go through it in a few different ways to hopefully have this make sense for you. So this is a build of a simple neural network. This is our neural network itself, and then we can see it's a 16-layer neural network, and then we have our feed forward mechanism that we have here, and then we create our data set. In this instance, we're creating our 2 moons data set. and then we have 1,000 samples, and then we put a little bit of noise in there as far as our dropout, and then we train the model using our atom optimizer, which will be very standard. You'll hear that, and that will be common all throughout. And then we put our loss rate in there. And then this is where we put our vector quantization. So we run through our training, right? So this code up until here is normal and full, and is a full training of a neural network. We could run this code by itself, and then this would do a full training, like a full epoch training, right? I would have to do a little bit more just to make sure that it would print out, but that would be it. And then we could run this code on its own. And then so within this code below it, what we're doing is a second training on the model. So it's fine tune number one, fine tune or train number one in this instance, and then train number two. So you train it twice. And then you get the initial weights, and then it's boom, 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 and then you train based. You start with the initial weights that you trained on, and then you go from there. And then what that looks like when we train the model and we run it is this, right? So we want the loss rate, like if the loss rate were 1.0, 0.0, we would have 100%, right? And then so in this instance, it starts off 0.67 and then it goes down to 0.416. And then we can see again, it's starting off when we do this, this vectorization it starts off with the weights that it had from the beginning, right? So these are its ending weights from its first training. So it starts off and even a little bit better, and then it goes down. And then we can see the loss rate, it's not learning as well within this, right? Because it starts off at 0.67, goes down to 0.41. In this instance, starts off at 0.41, goes down to 0.33, right? So we have like almost 0.3 difference here, and then we have like not even 0.1 difference here. So you can noticeably see that the loss rate is not as good here, but that's expected, right? Like we expect some sort of performance loss, and then if you read through the paper, like their performance loss and their metrics on most models is around like 4 to 5%. That you can see as far as degradation, which is actually like super phenomenal as far as quantization. And then so, and I give you here as well, kind of exactly everything that is going on here, and then how to do this. And then I played around with this a little bit more. And then I wanted to see like, with anything that you do with AI, there's multiple ways that you can do it, right? There's not one way to do it. And this is a large portion why I think that like there's not money directly in AI. And I say this a lot, right? I think people don't understand this. And let's say that like someone comes up with a very unique concept. Let's say VPTQ. Right. And then so this is VPTQ and the concept that they come up with. Right. And then so this person, they come up with this and they say, hey, I'm going to patent VPTQ. And then boom. Right. And then I can just come along and then say, okay, I'm going to create independent layer quantization, and I'm going to call it ILQ. And then ILQ is literally VPTQ, but it applies to independent layers as opposed to the full layers. And then so if you look here, it's the same code with our simple neural network, right? This all stays the same. This here is just the simple setup for the neural network as before. But then here we have so this is the difference in equation, right? And then if you look at this equation here, this equation is completely different than this math equation that we have over here for this. This is actually a much simpler math equation, right? Far simpler as far as the math than we have in our math here, like much more complex. And then so like no one could say that these are actually the same, right? This is like mathematically speaking, these are not the same at all. Like they're completely different. And then so you can see like, so, okay, you invent and patent VPTQ, and then the next day you have ILQ. And then that's just how it goes, right? So just explaining that out. But this is just essentially a different method for doing this, but then within and running this, and then what you can see within this method and utilizing this method is we get actually like better results, like almost like more better accuracy overall at the end, right? And then arguably, and not arguably, but like actually noticeably, a better loss rate in this instance. We go from 2.29 to 0.18, so we go like more than one, whereas in this one we're going from 0.41 to 0.33, which is obviously less than one. So very straightforward there. And then, so how this model works again is, it quantizes these weights and then it uses a lookup table, right? And then, so the very last thing to show you and to illustrate here is that lookup table process. And then it's very straightforward. And then, so again, this is using k-means clustering. And so it's a machine learning algorithm and a very common machine learning algorithm. Like if you, I'm utilizing these terms and then just going through, if you watch enough videos and you go through these concepts enough, all of this starts to stand out, and it's all the same concepts over and over again, and it really is, right? And then that's all there is to it. It's all math. And then so within this, essentially, what we're showing is that we have our what our centroids would be in this instance. Again, we have the our word vectors, and then we use our k-means clustering algorithm to find the center of those word vectors, which is here. And then we turn those into a quantized weight based off of this formula. So 0.5 becomes 1, 1.25 becomes 2, minus 1.0 becomes 3. And then we create a lookup table and then so the model stores 1, 2, 3. And then when it needs to access that, it utilizes the lookup table and it looks up, it gives 1, 2, 3 to the lookup table. And then the output result is 0.5, 1.25, and minus 1.0. And then, so that's essentially how it works overall. Very straightforward, very simple to implement, and then reduces the complexity, the mathematical complexity of the models very significantly, which is what matters, like at the end of the day. This is how I'm assuming Apple is able to get like a model onto a cell phone, things like that. It's crazy math like this. And so it's understanding the math like this opens up the whole world of AI to you. Like if you can understand this and then go through and then understand exactly how this works and what this is doing, you can understand literally every single portion of AI. And so if you like this type of content, please like and subscribe. Thank you very much.